Okay, that was quite a lot to take in, but yeah, let's now talk about the last concept in this lecture, which is asynchronous algorithms. And to explain or to introduce asynchronous algorithms, it's useful to realize or to find out, to formulate or to just to realize that the algorithms I talked about so far, so federated gradient descent, federated averaging, federated prox, federated stochastic gradient descent, they are all algorithms of the same type in the sense they are all based on a fixed point iteration. So you can, for them, find operators, so you can write those algorithms as a fixed point iteration. In each iteration, you apply some operator, and this operator can be different for different nodes. You apply this operator to all the local model parameters that are currently used at the nodes. So these arguments here are the current local model parameters at all nodes. And you apply some operator, calligraphic F, superscript I. So each node I, the update at each node can be represented mathematically by an operator. And it might be a nice exercise to work out what is this operator for federated gradient descent? What is this operator for federated averaging? What is it exactly for federated prox? So did I show an example here? Yeah, I worked out the example here for gradient descent. So for gradient descent, the operator looks like this. It uses the gradient, of course, the gradient of the local loss function and these coupling terms. So this is an explicit this is one possible choice for this operator fi. And if you use this choice, the algorithm that you obtain is federated gradient descent. If you replace this choice with some other choice, you get federated averaging. So all these algorithms that I have talked about so far are based on this, I call it synchronous fixed point iteration, because they compute this fixed point iteration at each node simultaneously or synchronously. And yeah, so an federated learning algorithm is determined by its fixed point operators. So instead of writing down a pseudocode federated learning algorithm, you can just say, what are your fixed point operators? And you have clearly defined, or you have determined a federated learning algorithm. Okay, but this is challenging for several reasons. So implementing this synchronous update is intractable in many applications. For example, these devices that carrying out these updates might be very different. So some of them might be a laptop with a 2.4 gigahertz processor, while other nodes I might be a small Raspberry Pi with a clock of 1 megahertz, extremely slow. On the other hand, to implement this synchronous updates, you need to have these current local model parameters available. So node I, in principle, needs to know the local model parameters of all its neighbors, or in the extreme case, of all other nodes. So you always need, after each iteration, you need to submit, you need to update all your neighbors with your new model parameters. And this might not be possible if you have bandwidth constraints, or you might at some point have no connectivity, no coverage if you use Bluetooth connections or a wireless link. For some reason, the wireless link is out of usage. So you might have only outdated information. You might only have the local model parameter at one of your neighbors from the previous 10th iteration, but not the current one, because there is no connection anymore since 10 iterations. So we might want to use instead an asynchronous algorithm, which works like this. So it looks very similar to the synchronous algorithm. So it again uses these fixed point iterations, but in a slightly different manner. First of all, it uses this fixed point iteration not for using the current local model parameters, but it uses the local model parameters at other nodes from the past. So in particular, we have a delay which is given by k, the current iteration counter, minus this variables here, s. This is a bit heavy notation, but I didn't find a way around it. So this s superscript k I1 is the delay from node 1 to node I in the kth time step. So this might vary with k, might vary with I, might vary with the second superscript index here. This gives a lot of freedom, actually. So this is a very generic, very widely applicable model, asynchronous model. You can cover a lot of applications or computational settings with this. And by the way, it's not mine, so I didn't invent this, but this is covered or introduced, at least where I heard about it, first saw it in this book of Bertzekas. And in general, I can highly recommend whenever you want to learn about a certain topic, a certain field, try to find a textbook by Dimitri Bertzekas. And one of his textbooks is about this distributed or parallel and distributed computation, where he introduces or explains this asynchronous computational model in very good detail. Okay, so yeah, in this asynchronous algorithm, we allow outdated information to be used. So each update at node I, then update at node I can use the model parameters at other nodes from 10 or 100 iterations ago. So this delay can be very large. It turns out that for some algorithms can tolerate unbounded large delay. So this delay can grow to infinity without bounds, and still the algorithm works. Yeah, second difference to the synchronous algorithm is that here we have this update only for certain nodes at each time step. On the or in different words, this for node I uses this update operator only at certain time steps. In particular, these time steps t superscript I, which denote kind of the active times when this node was active, when this node woke up or had battery again. Then it computes this update. Otherwise, we assume that it just keeps the local model parameters it had unchanged. So it just stores the model parameters until it is able to be again to do an update. Okay. And yeah, so I have shown here one example for federated gradient descent. I mean, and this designing asynchronous algorithms is now pretty straightforward. You first need to find out what are these fixed point operators, how do these fixed point operators look like. For federated gradient descent, they look like this. And then you just insert this outdated information. You just do this update using these outdated local model parameters. And you only do these updates when the node is active, so during these active times or time steps. Yeah, again, I also have prepared here a demo, which you can check out, and I strongly encourage you to run this demo for asynchronous gradient descent. And yeah, when preparing these demos, I was so much made aware of how nice it is or how easier it is to implement asynchronous algorithms, because asynchronous means, in the end, you don't have to ensure synchronous operation. So it's not like something you must do. It means absence of synchronization requirements. So it's way easier, much nicer to implement an asynchronous algorithm than a synchronous algorithm. But then, of course, nice that you have an asynchronous algorithm. Yes, there's a question. Yeah, you have to, for example, if you have to store whenever node I here. So we look at node I and his updates or their updates. Whenever this node gets an update from another node, it needs to store it somewhere. It must not forget it. Yeah, this is a requirement. Yeah, which might be not reasonable. Also, it might not have the memory. But in this model, we assume that whenever this node I receives a local model parameter from another node, it is able to store it until it gets a new update from this node. Yeah. Very good point. So it must have some memory, and this memory must be non-volatile. So this memory must also persist in times where it's not active. A very good point. Yeah, so as I said, implementing asynchronous algorithm is like a piece of cake compared to synchronous algorithms because you need so much overhead and like you need in some sense develop infrastructure for the synchronization, like a synchronization server. And if you don't need to do this, it becomes so much easier to implement these distributed algorithms. However, you might not have the performance or the statistical properties. So we have here different notions of asynchronous algorithms depending on how much they can tolerate. For example, an algorithm is called totally asynchronous if it works in a sense that can be made precise in different ways. For example, we say it works if it still converges in the end to a solution of GTV minimization. Let's say this is our definition of works. So then a totally asynchronous algorithm works if the active set is infinite for each node. This means that there is no node that at some point stops. So if we wait sufficiently long, each node will at some point again be active. There will be never a time point beyond which the node stops doing. So it will never die, so to say. And this is quite a minimum requirement. It must be participate as long as the algorithm runs. And the second requirement is that these delayed update times are also unbounded, which means that there's always at some point where each node will send to every of its neighbors one update again. So there's no time step beyond which the one node doesn't send any updates to one of its neighbors anymore. So these two requirements basically say the algorithm is poorly but still working all the time. So it basically says no node is dying, so it always at some point again does an update, and no connection is dying completely. However, the connection might be very poor, leading to a lot of delays. So the amount of delay does not necessarily need to be bounded here. So this delayed update times must be unbounded, but the delay, so how much they can lag behind the actual time step k, can be unbounded. But still, they must never stop to send once in a while an update to its neighbors. And yeah, totally asynchronous algorithm works only if these two, I would say, minimal assumptions are satisfied. There's a question. The latest one, yeah. Whenever a node I prime sends an update to node I, it overrides the latest update from this node. It always keeps one local parameter for each of its neighbors. Yeah, so these updates are overwritten. They override each other for each neighbor. Okay, and then there's a second notion of asynchronous algorithms, which is a bit more requires more. It's kind of in between totally asynchronous and synchronous. There's partially asynchronous. So we say an algorithm is partially asynchronous if each node wakes up at least every capital B time steps. So this capital P is asynchronous measure. The larger this B, the more asynchronous the algorithm is. So in the extreme case, if B is 1, then this means synchronous. It's the extreme case, but B can be much larger than 1. Yeah, so the requirements for a partially asynchronous algorithm is that each worker wakes up during each B time steps or events at least once, and the delay from each node to each of its other nodes cannot be larger than B. So we have a bounded delay. Yeah, I show here this hierarchy of asynchronous algorithms. So we have this totally asynchronous, which is our large family, all kinds of algorithms, a large class of algorithms can be totally asynchronous. And then we have these partially asynchronous algorithms with different levels of asynchronous measure B, capital B. Okay. So now the question is, now that we have characterized this totally asynchronous and partially asynchronous algorithms, nice, but when do they work? So when does a partially asynchronous algorithm converge to a solution of GTV minimization? And this depends on two things. First of all, it depends on the fixed point operators. And these fixed point operators, they are defined by the algorithm that you use and by the loss functions or the edges, so by the federated learning network. So I told you in the beginning, this federated learning network includes loss functions and edges as design choices. And all these design choices have an influence in how these fixed point operators look like. So this fixed point operator, for example, for federated gradient descent involves a parameter of the algorithm, the step size eta, involves local loss functions, and involves the structure of the federated learning network via these neighborhoods and edge weights. So all these components determine how these fixed point iterations look like, how this operator look like. And this, of course, the properties of these fixed point operators, they decide when does an algorithm work or not. But of course, it not only depends on the fixed point operators, but it also depends on the asynchronous computation. So how much asynchronous is the algorithm? And this is characterized by the update events, TI, and by the delays. So we'll quickly go with it for the sake of time. We're running out of time. So it turns out one way to characterize or to provide sufficient conditions on asynchronous algorithms is using the notion of pseudo-contractions. So whenever these fixed point operators are a pseudo-contraction, which means that if you apply these operators to a given choice of local model parameters, and this operator pushes them more towards the solution of GTV minimization, which is very natural. I mean, in the end, these federated learning algorithms, they repeatedly apply fixed point operators. So of course, you want the result of these fixed point operators to be closer and closer to the solution of GTV minimization. So this is a very natural requirement. And it turns out that if these fixed point operators are a pseudo contraction, then you have one. Once you have proven that for whatever choice of local loss functions, edges, and algorithm, federated learning algorithm, the resulting fixed point operators F are a pseudo contraction, you have one. There's a beautiful recent paper from authors, I think they are from KTH Stockholm, that shows that as soon as this is a pseudo contraction, it is totally asynchronous. And you can also work out explicit convergence rates in terms of the asynchronous measure. So you can tell how fast, how quickly do these local model parameters of this federated learning algorithm converge to the solution of GTV minimization. And this convergence rate involves this asynchronous measure in a very natural way. So it's this B is here. The larger B, the smaller you make this exponent, and the slower is this convergence to distance zero, because in the end you want your model parameters to have distance zero to the solutions of GTV minimization. After all, our principle is that we learn model parameters that minimize GTV. We solve GTV minimization. So we want these iterates that we get out of this algorithm to get closer and closer to the solution of GTV minimization. Okay, so the question now is, how can we ensure this? It's nice. So we found out that if these fixed point operators are a fixed point, a pseudo contraction, it works. But how can we make sure that it's a pseudo contraction? Well, this is the hard work. This is the hard work where you need to analyze this fixed point operator for your specific choice of local loss functions, of edge set in the federated learning network. All these properties or these design choices influence this the fact or influence if the resulting fixed point operator here is a pseudo contraction, and what is this contraction parameter kappa, which should be very small. The smaller this kappa, the better. Okay, that was quite a lot to take in today. I will skip now the questions for the sake of time this time, just to wrap up. So we have introduced several widely known or popular federated learning algorithms, and it turns out they are all of the same type or the same formalism in being fixed point iterations. So federated gradient descent, federated averaging, federated procs, you can write them as such a fixed point iteration. And the fixed point of this operator f is a solution of GTV minimization. And we want then to compute the solution by applying this f repeatedly. And the convergence of this fixed point iteration depends on the contraction properties of this operator f, in particular if it's a pseudo contraction. And if it's a pseudo contraction, it turns out to be quite tolerant against asynchronous implementation effects. In particular, it can handle arbitrarily large delays between these clients, and it only requires, so it's basically it's totally asynchronous algorithm. It only requires that each client keeps on working for a while or after a while, so no client drops out completely of the federated learning algorithm after some time, and that no connection between two neighbors in the federated learning network dies off completely after a certain time. So there's always, after sufficiently long of period of time, a node wakes up and does again an update. And after a sufficient amount of time, a node is able to send its update to each of its neighbors again. Okay, what's next? The cliffhanger, so to say, for the next lecture is we will study some main flavors of federated learning, including horizontal and vertical federated learning, and we will see how those are nothing but special cases of GTV minimization again. So I hope you will appreciate more and more the versatile and flexible use of GTV minimization for all kinds of federated learning models, settings, and algorithms. Yeah, and again, as I mentioned, as I announced, we will also have next Monday, half of the lecture will be used for a guest talk by a researcher from Canada talking about the interplay between blockchain technology and federated learning. Yeah, thanks for your attention.